about tensor products. So this time let's talk about kind of very common tensor product, still related, so in this case related with vector space. Sometimes it looks like a scalar extension, sometimes not necessarily. So let me start with some examples. So for example, prove this is isomorphic to Q. And more generally, for ring R with this fraction field. Okay, so maybe this is the domain. This is isomorphic to K. So this map suggest. Okay. We could even generalize slightly more. This K is containing some field L and subfield, so this case L is like K vector space. This is isomorphic to L. As example, Q tensor over Z with real numbers. It's isomorphic to real number. And Z module. So here is R module. And so without proving this, let's directly prove some very general statement. So let R be a domain with fraction field K, and then let's take K vector space. And there is R linear isomorphism K tensor R with this vector space way as isomorphic to way. So in particular, this already contains this, all of it. Okay, this is already contained there. Nevertheless, we can still generalize a little. Let's say let R similar setting with fraction field. Again, we key vector space way. And now we take any non-zero R module. Let's call it M containing inside K. Then instead of K, we can modify this K to submodule it. This is still true. Again, adds R modules. And the map is in particular for any ideal of R, that theoretically this is containing fraction ideal of R also. This is R module containing fraction field. We have this isomorphism, right? And in particular also you have this so let's start to prove it. Mainly we prove this 2 and 3. The technique is very similar, you will see. Let's start with the first one. So obviously we always start with universal property to construct a map. So the key observation is that this multiplication map is bilinear. Just check it, because so multiply with R, it's just contribute once to it. With some things, okay, could imagine even what I want to say is I'm thinking about homogeneous polynomial, but okay, not here. So multiplication map is bilinear, and so it induces this map from tensor product two-way. And now you just want to check this is an isomorphism. So check it is surjective and injective. So obviously surjective as one is containing K, and so this is mapped to it. So now let's check the injectivity. Here comes the trick. The trick is that, so let's say X, so let's call this F. Suppose so first thing, any element of K tensor way is elementary tensor. Basically because suppose you have xi, vi, and then this is over R, right? And then the key idea is that actually you could even remove fraction to cross the tensor, because this is, and so if you by R linearity you move the S to the right hand side, you got this, right? And so this is, let's say Si over Ti and then Vi divide the argument. This Ti could also be moved to the right hand side, and so this is finally just Xi Vi, and so just this is the elementary tensor. So to show the injectivity, I only have to show that if this is 0, then this tensor is 0, right? But this is also, as I say, x way. Then x tensor way equals tensor x way. This is 0, so it's done. Okay, no problem. So let's say what happens for the slightly more general setting where we are not necessarily having the fraction field k there, but some module in particular might don't have identity there, and we might not have whatever denominator there. Okay, not in general. So let's start the proof. So again, let's start with bilinear map. And check this is bilinear. Again, the same idea, the multiplication is bilinear, so this is the map. Let's call it F. All right, and so let's check it. Check if it's surjective and injective. So remark. This might not be here, right? But still, for any small way in V, notice that although that's not there, but take whatever small m non-zero there, and then notice we have m tensor one over m. So this is in m, obviously this is in w because w is a k vector space. This is in k because w is in k, some module. And so this is in our m tensor w, and so this is a map to w. So f is surjective. It's left to show f is injective. So now the important thing is, again, we claim first this is has all elements elementary tensors. In other words, for any mi, wi with MIM and we are in weight, so you cannot simply say that it's SITI. You cannot simply move it to the right hand side, right? Because we don't know 1 over ti is in M or not. In general, it's not. What we do is that we can even make the left hand side with this component bigger, because M is our module. It's inside K. We find a way to multiply with elements of R to try to make the left hand side looks the same. For example, this is at least firstly ti over ti wi, right? And then notice that this vi over ti, this is still inside v because v is a k-vector space. And so you could move this ti to the left hand side, so this gives you si tensor R, so vi over ti. And now we just by multiply this si with some elements in M to make it the common one. So this is summation of A times some, let's call it si tilde vi over ti. Basically, I define this A to be the multiplication of all those si. And then this si tilde should be A divided by si. 1 over si tilde should be A divided by si. Anyway, so just saying that we could make it finally something, let's call it vi tilde of this form, so everything is elementary tensor. And so now suppose something is still, let's simply write it for arbitrary element. Of M tensor V. Suppose this is 0. Then what do we have? If this is 0, then by our construction, A times V equals 0, but this is the domain. Wait, this is our construction maps to V, yes. This is inside V. Say it's in R, so it's in V. Say it's in R, let's be more precise. Let's say it's in K. Let's see. This is a k-vector space. It's a k-vector space. If this is 0, then either the vector is 0 or the scalar is 0. In both cases, tells you that this is 0, so it's injective. And we are done.